Hello and good evening. I see Raj is. Oh, wait, hang on. There we go. We got Raj up in here and one other person, though I don't know who they are. This is our um, penultimate Chem 420 office hours. Um, I haven't. Check my email in a few hours. So I'm gonna double check to see if we have any pre-programmed questions. Though, if I were to put money based on past results, I'd say we probably don't. But let's see, none in let's see, none in Canvas. Wait, I feel like I saw. Oh, sweet. I have a question from Irwing. Let's see. Okay, hey Josh, I just want to ask you, do you think the mechanisms I used for are going to work? Okay, this is probably not a... Well, here, let me see. Let's see. Okay. Here, let's break this down. Totally. All right, Raj, let me do this email one first, and then we will hit up yours. Okay, so, this is a synthesis question. Let's take a look. So we're starting with a couple of rings, and we have a bromine hanging off right here. And then we're being asked to synthesize the following compound. All right, so here's the deal. Okay, so when you look at the beginning and the end, you want to identify what's changing, right? And when you look at what changes, everything about the molecule is the same except for this part. You can see that this portion of the molecule is unchanged, right? So what we're adding is we're adding one carbon. We're adding one carbon and an alcohol group, right? Where, actually, that's a little ugly. Where we started with just a bromine, okay? And so I have a proposed sequence of steps, and so let's look at the sequence of steps and why it may or may not work. So let's look at this. as a proposed, or a proposed sequence of steps. The first one is treating with magnesium. Right, second proposed step. Whoa. Hang on. There we go. Is a deprotonated alkyne. Third, whoops. It's H2 platinum. Fourth, hydrobromination. And fifth, fifth, is just the second step of the hydrobromination. All right, now step number, when I look at this sequence, step number 1 is looking good, right? This will form a Grignard. Which is a nucleophile. It's a great way to add carbons to your system. All right. The problem with this proposed series of synthesis steps comes in with the second step. The first problem is you'll notice that we have on that alkyne, we have 1, 2 carbons. But when you look at the number of carbons that we're adding to this molecule, there's only 1. So the first problem is this is too many carbons in length. We actually only need to add 1 carbon. And then the second problem is a Grignard's a nucleophile, and a acetylide ion, a deprotonated terminal alkyne, is also a nucleophile. And nucleophiles don't react with other nucleophiles. They only react with electrophiles. So So nucleophiles don't react with other nucleophiles. All right, so that is the biggest problem with this proposed synthetic setup, is turning the bromine into a Grignard is an excellent first step, but then we have to feed it an electrophile, right? Then we have to feed it an electrophile. And so a better way to go about this, so I'm just going to redraw. Whoa. Oh, there we go. Wasn't sure what happened for a second there. So redrawing my starting material. And my target. All right, so taking it to a Grignard is an excellent first step. All right, so go in magnesium and ether to form our Grignard reagent. Couldn't be better. All right, but then when you think about, okay, how do I take this piece and get it here? I only want to add 1 carbon. right? And Grignards are famous for reacting with carbonyls. So I want to have a C double bond O, and I only want there to be one carbon, which means that formaldehyde is actually the best choice, because once, when you think about this mechanistically, once this Grignard attacks that carbon, we're going to make a new bond between this carbon and this carbon, right? Here's our first carbon. Now we have a new carbon-carbon bond between these two carbons. And now, instead of C double bond O, we have a single bond to this oxygen, and it has an anionic charge. So we've made an alkoxide. And you can see we're almost there once you add formaldehyde to this Grignard. You're almost there. All you need is something to deliver a proton. So that third step is anything with an H, which, like water, is a good choice. You could do H plus. That last step, it doesn't matter. But this would be the way to go to get from part A to part B, because we have a bromine, we can make a Grignard, but then we only want to add one carbon, so we need to add a carbonyl that only has one carbon in it, so formaldehyde has to be the way to go. And then we just protonate it right there at the end. So anyways, that was my analysis of the proposed synthesis scent, and then this is why this would be the 3 steps that I would pick to get from our starting substrate, our initial substrate, to our final product. Cool? All right, so now we're ready for Vraj's question. All right, let's see. UV spectroscopy of organic compounds is usually concerned with electronic transition. Ah, okay. So, a little bit of what we talked about in Chem 400. Unfortunately, okay, so we didn't have time to cover any molecular orbital theory this semester. We just managed to squeak through with intermolecular forces. But so some of this we've talked about, but some of it we haven't. All right, and here, give me 1 second. So, all right. So usually with so just a little bit of background here, Raj. So we have talked about making bonding orbitals. Right? We've talked about bonding orbitals like there are sigma bonds, I'm just going to call them sigma and pi orbitals, right, that house electrons. Well, and again, we didn't talk about MO theory this semester. Normally I do, but we didn't have time to get to it. Turns out every time a bonding orbital is made, you also make something called an antibonding orbital. And your bonding orbitals are low in energy. Your antibonding orbitals are high in energy. Actually, need to erase some stuff. So you have your sigma bonds are typically lowest in energy. Then you have pi. Then you have your antibonding orbitals. You have pi star and sigma star. So those are your high energy antibonding orbitals. And if energy is the y-axis, you would line them up like this. Yeah, and then exactly, the higher in energy something is, the less stable it is. Yeah, high energy equals unstable. All right. And most organic compounds are not UV active. However, some are. And yeah. And so if we were to put like electrons up in here, I'm going to make this one a different color. The transition in UV vis takes an electron from its bonding orbital and promotes it to an antibonding orbital. And the gap that you see in UV vis spectroscopy is usually you usually see transitions when it does happen from pi to pi star. Like I said, most organic compounds aren't UV active, but the ones that are have extended pi systems, and it's the pi to pi star transition that you usually run into with organic compounds. Totally. And so this is something that would be covered usually in the aromaticity chapter. Well, it's not so much that we're adding energy to bonds. Per se. It's more along the lines of the atomic absorption stuff. So remember, like, the atomic absorption stuff that we talked about with hydrogen, where an electron in a lower energy orbit would get promoted. It would absorb light and then move up to a higher energy orbit. Then it would jump back down and release the light. That's the kind of thing we're talking about here. It's just that instead of looking at one single atom, we're looking at a molecule. So certain molecules can absorb ultraviolet or visible light, and when it absorbs that energy, it promotes an electron from a lower energy bonding orbital like pi up into a pi star. So it absorbs it, and then that electron jumps back down and it releases that energy. And so typically UV active or UV vis active compounds have very vibrant colors because they're absorbing light energy from their surroundings and then releasing that energy. And we see that as color. So it's better to think about this as not so much the bonds absorbing energy, but the whole molecule is. And the way it absorbs that energy is promoting an electron from a low energy orbital to a high energy orbital, just like we saw with hydrogen earlier. Okay, so let's see. So let me look at the options. Organic compounds is usually concerned with which electronic transition? Not sigma, sigma star. Yeah, I would say yes, E, because it includes non-bonding to pi star and pi to pi star. Yep. Oh, thanks, dude. I so appreciate that. Yeah, no, well, and the thing is part of it's probably like I know where to go, whereas you read this problem and you're like, I have no idea what this relates to. What are these weird things? And I'm like, oh, well, he asked me about this, so I know I need to tell him A, and then I need to tell him B, and then he'll be able to draw the conclusion C. So I just know the places to go to. I think it's just because I've been doing this longer. I don't know if you watch Star Trek, but there's this alien entity named Q. It's this like giant like space consciousness who's been around for like eons and doesn't die. And it's not that he's a super genius, and it's not that he's like omnipotent or anything, but he's been around so long and has seen so much that he seems like he's all knowing. And I think that's the impression I'm giving here. It's not that I am chemistry all knowing, or the reason why I make it look easy is because I've been doing it for 15 years, which is if you think about how old you were when you were 15 or 15 years ago, I probably. I think I've been doing this since you were like 3. So anyways, I think that's part of why, or at least that's my best guess at the moment. I'm actually kind of surprised none of the Chem 420 crew has surfaced yet, because I'm writing an exam they have to take on Wednesday. All right, let's see. Where do the proteins go when they are injured? Where? That's awesome. Yes. Oh, hey, Mallory. I am writing the late lab exam. How difficult is it going to be? Unclear. I'm unsure. I don't know. I mean, it's so. So here's what I know. Let's talk about what I know about the late lab exam. Oh, let's see. Oh yeah. Dude, totally. Dude, no worries. Okay, so here's what I know so far. Because I'm like I said, I'm still in the thick of writing this thing. So I haven't made it very far. Mostly because I'm also giving I am giving on the same day a Chem 400 take home exam and a Chem 400 multiple choice exam. So those got written, and now I'm working on ours. So here are the things that I know. First, it is you'll have it'll be 3 hours. You'll have 3 hours to take and do it. So one lab period. And I haven't received a lot of what's the word I'm looking for? Like, I haven't received a lot of input's the wrong word, or maybe guidance from Mac is not Mac. Oh my gosh, Max. Mac is my kid who's turning 2 in like a couple months. So I say Mac a lot more often than I say Max. He asked me to write it because I guess he like pulled the class, and not everybody in the late lab could take it during the early lab exam time, and so he didn't want to make it the same because then the exam could leak and the late lab would have a significant advantage and all that stuff. So he was like, "Hey, could you just write one? That way we know they'll be different, and that way we don't have to worry about it." So and that I didn't hear anything as far as like, "Oh, how long are you making it? What types of problems do you like in a lab exam?" I've only ever written lecture exams for OChem. So writing a lab exam is a little bit new for me, and so I'll kind of give you an insight into my thought process, at least so far, and also tell you the concrete things that I know. So first is you'll have the full lab period to complete it, and when I say 3 hours, I mean explicitly, I mean 6 p.m. to 9 p.m. So it'll be made available. I'll upload it to Canvas at 6 p.m. You can download it, take it, return it to me by 9. The second thing is I'm not writing an exam that's supposed to be 3 hours long. So you don't have to worry about, like, am I writing 3 hours worth of a test? Totally not my intention. I am, excuse me, I've got the hiccups all of a sudden. I don't know if it's nerves or what, but, so 3 hours to take it. Content wise, I'm basing the questions on the lab experiments. So I'm basing the questions on the experiments that we've done, and I'm focusing on the post-Rona labs. All right, maybe rather than post-Rona, I should say online. That might be better. So I'm focusing on the online labs that we've done. So that's been my focus so far. I have like so now this is where I become less certain, but mostly because I have less done. I think I only have like I've got 3 problems kind of crystallized. So I mean, when you look at the syllabus, the post coronavirus labs that we've done have been like the nucleophilic substitution reactions, the PIMOL activity one. I'm not going to have you guys do JChem Ed, not JChem Ed. I'm not going to have you do calculations during the lab when like with the 3D structures optimization, that sort of thing. We've done the radical chlorination lab, and then the GC computational lab, and I believe that was the last thing we've done. Like I went through the announcements that both Max and I have made, and those are the ones that we've covered. So when you want to talk about like content, so far I have a problem. So there's sorry, let me pull up my syllabus again. So experiment 9.1 was a nucleophilic substitution lab. Right, 9.1. There's a problem based on that lab. I also have a problem so far based on the radical chlorinations. So that's definitely covered. Honestly, it's been a challenge to write this thing because I feel like when I look at what we've done post the coronavirus, it's really been, there's like the radical stuff and that one nucleophilic lab, and we haven't done any labs beyond that point. So I'm trying to come up with creative ways to test on this. If you're looking for if you're like, what should I review? I mean, these are the 2 things so far. As I know more, I will totally post more on our Canvas page. I'll post more specifics about turning in the material. I would definitely recommend review the radical chlorination lab questions, especially the stuff if you're looking for a good hint. The stuff on relative reactivity. The stuff on relative reactivity with primary, secondary, and tertiary hydrogens. There's a problem that I think's a little on the tough side. Well, there's a problem that has 3 parts to it, and Mallory, I feel like you have a little bit of an insight more than a little bit. You have an insight into how my brain works because we had Chem 400 together. So there's a problem that I have written that has a part A, B, and C to it, and part A is a underhanded pitch, like easy. Everyone should be able to hit that. Part B is a little harder. The pitch comes at you a little faster, but most people should be able to connect ball to bat. And then part C is challenging, is harder, totally doable, and again you'll have the full lab period to do it, so 3 hours. But not everybody may be able to actually get part C of this problem. So I would also expect. So I'm to kind of give you an insight into how my brain is working. I'm asking my questions like, okay, well, what can I test on? What content is similar? There definitely could be a few. So I would there. I haven't written it yet. I've written like 3 problems, which you don't want an exam, a 100-point exam, to be worth 3 problems because then each problem is going to be worth like 34 points. So it's gonna be more than 3 problems long. I would definitely expect mechanisms to show up. There will probably be more than one mechanism problem. So mechanism problems, specifically, definitely like radical. Mechanisms, possibly a nucleophilic. Substitution mechanism or mechanisms. It's we haven't really done anything. The interesting thing, ironic thing is we haven't really done anything with synthesis in lab, so I don't think I'm gonna put any synthesis stuff on there. And again, if I do, I'll let you know. But you guys have been hitting that more in lecture. We really haven't talked about it in lab, so I'm trying to focus the problems on content related to lab stuff, either direct stuff, like, oh, we did this in lab, and so you see these results. How would you interpret them? Or possibly, we did a radical chlorination. So can you know how to write the mechanism for a radical chlorination? Or we did some nucleophilic substitutions. Here's a weird problem. Like, you're doing nucleophilic substitutions, you get this unexpected product. Can you draw the mechanism for it? That sort of thing. So anyways, I honestly, that's, I guess, one other thing that we do know, or that I do know at this point in time. The lab exam is worth 100 points. All right. And so if something's worth 100 points, that also kind of dictates, in my mind, how many problems it should have. Because like I said, if it's 100 points and you only have 3 problems, each one's worth like 33 points. That's a lot of points writing on each one. 5 gets a little more manageable, right? 100 divided by 5, each one's 20. If you divide them by like 6, now it's down to like 16 points a problem. So there may be, again, I'm a little unsure, but I would expect the problem count on this exam to be somewhere between like 5 and 7, probably. Anyways, I'm not looking to destroy anyone. I definitely want to have problems on there that everybody will be able to get. I definitely want to have problems on there that challenge people. Oh, okay, here, question. You had a hard time calculating the statistical monochlorination from post-up 1. Oh, okay, yeah. Absolutely. That is an awesome question, Mallory. Let me pull that up. All right, so let's take a look. That's something productive that we can do. So okay. So this is from whoa, sorry, I just whacked my microphone. Whoops. No. Let's open a new slide. So with lab 8.1, we had this substrate. We treated it with radical chlorination conditions, and when you look at this substrate, we can see just by looking at it that there's a finite number of unique radical chlorinations we can do. This will generate 1. If we chlorinated it up here, it'll be the same. There's 2, 3, and then 4, right? No matter which methyl we chlorinate on the end, there's only 4 unique monochlorination products, right? So there are 4 monochlorination. Products we can form. All right, and so in the data analysis, when it says calculate the statistical probability for the formation of the 4 monochlorination products, so this is from the data analysis. This is part 1 from the data analysis. When you're asked to calculate the statistical probability, for example, if you look at position 1 on your alkane, there's 2 methyls that represent position 1. And for that position, we when you look at the number of hydrogens there, it's 2 methyl groups. Whoa. Or here, let me start by giving a more general expression. For the statistical probability, just based on the probability based on pure statistics, that equation is equal to, or actually, I need to make a better use of this space. That's where the lasso tool, there's nothing like it on a whiteboard. So the statistical probability for chlorination to happen at each position is equal to the number of H's at that position divided by the number of H's in the molecule. All right. And then, times 100. But that's how you calculate the statistical probability. So we have 4 different monochlorination products. And for the first monochlorination product, we're dealing with 6 hydrogens at that position. For the second monochlorination product, there is only 1 hydrogen at that position. For the third, there are 2 H's at that position. And for the fourth, there are 9. All right. Now we take each one of these and divide by the total number of hydrogens in the molecule. So that's 6 plus 1 is 7, plus 2 is 9, plus 9 is 18. So our total number of H's, 18. We do this for all of them. And then we take this and we turn it into a percent. All right. So the statistical probability then of a chlorination happening on the oh wait, hang on one second. Okay. So the statistical probability of chlorination happening on the first site is there's 6 hydrogens on the first site out of the 18 that are in the molecule. So there's a 33.3% chance of chlorination happening on that site, statistically speaking. The second site, there's only 1 out of 18 hydrogens. So there is a 5.56. I'm just going to go with 5.6% chance of chlorination happening at that site. Third site, there's 2 out of 18. There's a, statistically speaking, 11.1% chance. Finally, for the last site, there's 9 out of the 18 available H's that we could chlorinate. So there's a 50% chance, statistically speaking, for that fourth site to get chlorinated. So these numbers right here are based on pure random chance. All right, pure random chance. Now, Mallory, quick question. Oops. Would you like me to walk through the experiment 8.1 Um, that is correct. That is correct. Those percentages are not including the stability of the radical at all. This is just what we'd expect if we were just picking a hydrogen at random based on the total number of hydrogens available. But as you know, it's more than just random chance. That has a definitely plays a role, but the relative reactivity of each site also has a okay, good, awesome. I mean, not awesome that you had our time with it, but we can do it. We'll rock this together. I just didn't know if you like just said that part or if you wanted to see the rest, because I didn't want to drone on and on and on. If you're like, yeah, I know, I get it. But if that's material you want to see, I'm more than happy to go through it. Okay, so that's step one, and this is just the pure statistics of it. Nothing to do with the reactivity of secondary versus primary versus tertiary. All right, now we're given. So in the lab, we're given the 4 monochlorination products, which I'm going to write up here. All right, this first guy, I'm going to label as number 1. And then this guy, I'll label as number 2. Again, these are coming in no particular order. Number 3. Looks like this. Then last but not least, but not least, is number 4. And in addition to their structures, we're given their boiling points. So the boiling point of number 1 was 149 degrees. Boiling point for number 2 was 154 degrees C. Number 3 has a boiling point of 147. And then finally, we had a boiling point of 158 degrees Celsius. Okay, so this is part number 2 of data analysis. The reason why I'm writing this up is it says assign each pink peak found on the GC trace to its correct corresponding structure. And we're given here so a little chart that I'm going to recreate with peak retention time, in minutes, and then relative peak area. All right, and do my best to make a little grid here that's not too terribly wonky. So we have what we call peak A, B, C, and D. Then we have our retention time. Peak A, 4.22 minutes. Peak B, 5.32 minutes. Peak C, 8.94 minutes. And then peak D, 9.02 4, 8. And then we had a relative peak area of 190.3, 118.9, 142.7. Oh, sorry. That's the last one. 142.7, and then 214.1. All right. Now, with part 2, we're told to assign each peak to the GC trace, or assign each peak on the GC trace to its corresponding structure. And the thing that you got to remember is retention time on a GC is determined by the boiling points. The lowest boiling compound comes off the GC first, has the lowest retention time. The highest boiling compound comes off the GC last. So I messed up my boiling point down here. There we go. So to assign our GC peaks, we simply need to assign we do this based on our boiling point. So the lowest boiling point is number 3, right, with 147. So peak A is compound 3. Next, our next lowest boiling is compound 1 with a boiling point of 149. Next, let's see. So we've done 1, we've done 3, between 2 and 4. 2 is 154, so that'll come out first. And 4 has the highest boiling point, which means it will have the highest retention time. So that is assigning the peaks to the structures. That is part 2 of the data analysis. Now part 3, based on the relative peak area, calculate the percent of each monochlorinated product in this mixture. All right. Now to calculate the percent based on peak area, this is going to be the you're going to take the relative area of each compound divided by the total relative area of all of them. Then we're going to multiply by 100. All right. So our total relative area will be, let's see, 190.3 plus 118.9 plus 214.1 plus 142.7. Oh, wow. Well, this adds to a fun number. If we're doing sig figs, we gotta add a 0.0. Maybe that'll make it a little more palatable. But if you're superstitious, I'd consider this a bad omen and abandon hope all who enter here. All right, so that is our total relative area. To calculate the percentage for each compound, we need to take the relative peak area. So for compound number 1, for example, we take the relative peak area, which is 118.9 divided by 666 times 100. All right, that gives us a percentage for number 1 that is 17.9. Yeah. Totally. So 17.9 is the percentage of number 1. For number 2, we look at number 2's relative peak area. So 214.1 divided by 666 times 100 gives us a percentage of 32.1%. Looking at number 3, that's 190.3 divided by 666. So that'll give us a percentage of 28.6%. And then number 4, we do 142.7 divided by 666 times 100 is 21.4%. All right, so that is, oh, sorry, dropping my phone. That is the percentage of each monochlorination product in the mixture based on the relative peak area. Now, this provocative question, do the percentages calculated in part 1 match the percentages calculated from the peak areas? Can you explain why they're different? And when you pull those up, so make things super messy for a little bit. Whoops. So, for example, number 1 in the statistical analysis had a 33% chance of forming. All right? It has a 33% chance of forming, statistically speaking. But then in our calculated analysis, it's only 17.9%. All right? And if you look at all of them, they're all going to be different. And you already know the answer. Can you explain why they're different? The answer is that it's not just the statistical abundance of hydrogens at each position that determines how much is made. It's a combination of the abundance of hydrogen at that position with the reactivity of those hydrogens. How stable is that radical? All right. So the reason why the actual data is different than the pure random chance approach is because the most abundant hydrogen statistically is not the most stable radical. And both of these things have a guiding hand in determining the distribution of our products. All right, so that is the answer to number 4. Number 5, which monochlorination product is formed from the most stable radical? Well, we know that when it comes to radical stability, we know that tertiary radicals are more stable than secondary radicals, and secondary radicals are more stable than primary radicals. So the most stable radical would be a tertiary radical, and we know that the termination step in this mechanism, the termination step is when you have your carbon-based radical, R dot, collide with your chlorine-based radical. These two come together, terminate, and make your monochlorination product. So whichever product has a tertiary chloride came from the most stable radical. So the product formed from the most stable radical will be this one. And I'm going to lasso this over to the right side of the board. And the reason why is because this product, this product was formed by the reaction, whoops, we got a methyl group there, of this carbon-based radical with this chlorine-based radical, they combined to form this product. It came from the tertiary radical, so this is the product that was formed from the most stable radical intermediate in this reaction. Now, question, is this the major product of the mixture? Explained why or why not? Well, let's go back and find this guy in our analysis of the GC data and check this out. Here it is. Oops. No. Here we go. Here, whoa, sorry, I chopped the guy's head off. There we go. Here's the product that was formed by the most stable radical. Is it the major product? And when you look at the percentage, the answer is no. It's actually the most minor product. How could that be? Why is the product formed by the most stable radical a minor product? All right. So we know it's not. The explanation why is there are two things that govern your product distribution for radical chlorination, radical halogenation reactions. One is radical stability. Great question. Sadly, I do not. Sadly, I do not have these labs graded yet. So with this product, it came from the most stable radical, but it is a minor product. It's not the major product. And the reason why is there are two factors that determine product distribution for radical halogenation reactions. And those two things are, one, radical stability, two, the statistical availability of hydrogens. How many hydrogens are present at that site? And even though this one is the most stable, there's only one hydrogen present, right? There's only one hydrogen at that site. So that's why it is not the major product. One thing I would like to point out, though, is if you look at the statistical chance of that product being formed, number two, statistically, it only has a 5.6% chance of forming. And when you look at the actual product distribution, it actually represents 18% of the product formed. So it's in a severe minority from a statistical standpoint, but its stability boosts it by like 12.5%, right? Boosts it from 5.6 to 17.9%. So that is the explanation for why it is not the major product, but it's still better than we thought. All right. Okay, so question. Mallory, do you want me to work the post-lab questions? I'm totally down. I'm just not sure if it's a thing you wanted me to do. Okay, awesome. Awesome. Cool. Cool beans. Dude, how have things been going in lecture? Every once in a while I'm looking at I take a peek at the Zoom lectures that are posted later, and they look super rad. I haven't had the time to keep up with all of them, but the ones that I have watched have been fun. It's been like a cool nerdy science podcast is what it's felt like to me. It's like totally my jam. Oh, let's see, Raj. Question: is the ACS due today for you? Let me check the syllabus. Because I don't know off the top of my head, but my syllabus does. Let's see. Chem 4 hundo. Let's see, what's the yes? Yep. Last minute tips for the Chem 400 exam. Um, um, let's see. Study for it might be my last minute tips. One thing I can definitely say, you can also get last minute tips on in our live stream on Wednesday. Right, we're streaming 11:30 to 1 ish. So there's definitely going to be a chance to get some last minute questions in there. The multiple choice will be easier if you have all the Vesper stuff memorized. So if you can look at a molecule and go, that's the hybridization, that's the geometry, that's the bond angle. If you know that off the top of your head, you'll have the multiple choice timed Canvas test will be easier. So that'd be, I guess, my last minute tip is know your stuff. And again, I don't know how helpful that is, but that's the thing that comes to mind. Yep, or have it handy. That is also a viable option. It's the beauty of take home, right? Is you have more resources available to you than if you were sitting in a room with a closed door with me making sure you're not on your phone. Oh, well, you know, I don't know. I actually kind of feel weird handing out my tests to people who aren't in the class. Um, so, and also too, I don't know. Um, I actually don't know how. I don't know how good of preparation it would be for taking the MCAT test specifically, just because it's formatted so differently. Um, but if you want to get your hands on some of my tests, maybe I'll be fortunate enough to be teaching the OChem class you take. Who knows? But I actually am going to keep those copies in reserve for the students who are enrolled in the class. So I'm going to uh, decline that request. No worries, dude. Thanks for being so cool. Alrighty, are there any? Oh, let's see. Oh, Mallory, great question. Here, I can. Yes, I have actually. I actually. Funny you should ask that. Um. Later, dude. Thanks for dropping by. Mallory, actually, it's funny that you should ask that. Today, they literally just sent out an email, maybe like 3 hours ago. Um, uh, that faculty. Um, we just got word today that the fall will be 100% online. Um, um, oh, that's a good question. That is a good question. Um, I will have to get back to you on that, on how you'll be able to get your locker stuff, because I realize like some students have like goggles in their lab coats that you just store in your lockers. So I will figure out how you guys can get that stuff. Because I don't know what the correct procedure is. Yeah. Yeah. Um, they made that call just today, or at least told us about it. I know Sierra College had already decided um, to go online for fall 2020, and yeah, the decision just came through official channels to us faculty. Um, and I'm on you know the the I'm on the near last to know, because I'm in the adjunct faculty circle, but we still get to know before students. So yes, so we will all be electronic through the summer and through fall of 2020? That is another great question. Part of the challenge with online instruction for organic chemistry is there are a lot fewer resources available for laboratory stuff for OChem than GenChem. GenChem actually has there's quite a few different options available for kind of doing an electronic online lab type situation, and there's not as much available for OChem. So I cannot speak directly to how, for example, so you're going to be moving into 421. I can't say anything definitive about how the labs will be taught with 421, because it'll be taught by a different instructor, and so each instructor is kind of developing their own kind of material to meet the curriculum standards for each class, and we all have slightly different styles and ways of doing this. So I don't know off the top of my head who's teaching it, and whoever is will have a different, possibly a different take than Max and I have had. It might be similar, could be the same, could be different. It's there's no way of knowing, but I think at least the plan, because we were with this semester totally kind of blindsided. When I say we, I mean faculty. It went from hey, low key make plans to maybe go online because we might have to in like 2 to 3 weeks to it's happening in 4 days. And you know what I'm saying? Like it accelerated so quickly. So we were kind of scrambling, trying to do the best we can with the time we had. And there was the idea or intention early on of faculty going into the labs ourselves and making videos of us doing the experiments. So at least you guys could watch and kind of see the setup and go like, oh, okay, that's how you do that, and that's how you do that, and then we'd upload these videos to YouTube. That was the kind of initial plan or intention, but because of how fast things locked down, we weren't able to get in there in time and record stuff before there's the mandated campus shutdown, lockdown, lockout type thing. So faculty haven't had access to our offices, classrooms, labs since quarantine started. So I know there's been some talk of possibly when things start lifting quarantine, what's the word I'm looking, when quarantine is lifted and kind of the regulations are loosened up a little bit, faculty may try to make it back into the labs and make those videos of us doing the labs. So that's one possible format you might be seeing in the fall is YouTube videos of us doing the labs. You can watch them, you write down the data, and do the lab reports that way. But I don't know. Part of it depends upon, will we have access to the labs, and then will we have access to the labs when we can film in there, and all that kind of stuff. Also, all the experiments take setup. I don't know what staffing with like the stock room is looking like. So that's one. Sorry, Mallory. This is a very, very long way of me saying I don't know what the labs will look like, or if they'll be similar to the way they are now. One configuration that's a possibility is having videos to watch and then being assigned a set of data to interpret and write up. But I don't even, that's not even a guarantee, just because so much is uncertain and we're all kind of new at this. So that's one possibility, but we'll have to wait and see. I don't know exactly how things will be going down in the fall, other than we're going to be all online, which is weird to think about. Like from March. Yeah. Okay. Good. I'm glad. It's bizarre. I've known for a few months now that the class that I'm teaching over the summer is going to be online, but just getting that final news today that the fall semester will be electronic. It's like, whoa. For most of the spring semester, all of summer, and then the entire fall semester, I'm going to be teaching it from my office in my house. Like it's weird. It's weird. Like I feel like I don't go places anymore. And I guess that's the way quarantine's supposed to feel, but it's just weird. This is a weird time to be doing this, all this stuff. So yeah, probably the longest I don't know answer ever given. But that is the truth of it at this moment in time. Have you been hanging in there? Have the online lectures been going? Is one thing I've been wondering, because I like, as you know, I've been using YouTube. I haven't been using Zoom, and I've been enjoying YouTube as a lecture format. Oh, dude, yeah. Oh my gosh, yes, totally. Totally. I can't even imagine what it'll mean for sports. It's got to be nuts. So what? I mean, just so much of the things that we just take for granted, aren't available or changing. Like even my brother is actually this is his finals week right now. He's at Berkeley, and this is his last semester of his senior year at Berkeley, and so he's graduating this year. And obviously, they're not holding a commencement, right? Because you can't gather that many people together in one place. But he was telling me that there's a group of let's see. Yeah, totally. Totally. I have definitely felt the difference. The difference. There's something about the in-person interaction. I think there's something about that in-person interaction that is so much more conducive for learning and teaching. At least in my opinion. I think it's harder to ask questions. When someone is lecturing. You know? It's funny, I did a survey of my Gen Chem students, just like a poll. I wanted to like see how things were going, see what was effective, what wasn't, and I asked a set of questions, and I got like really good response rates too. Like 90% of my class responded, so I can feel fairly confident in the numbers. But I asked them to rate from 1 to 5, 1 being horrible and 5 being awesome, how effective lecture was before and after Rona, and then how much they enjoyed lecture before and after Rona. And what was so funny is after, like, electronic didn't get bad. It was like the effectiveness was like around like 3.5, and the enjoyment was around like, I think it was like a 3.3. But before coronavirus, so in person, it was like a 4.5 and a 4.3. Like, and it was the same. It was like a 1 point dip. Like, it went from 4.5 to 3.5 before and after. People thought it was more effective before by 1 full point, and then they thought it was more enjoyable also before by 1 full point. That's how it averaged out. And so I think, you know, like, we're, as faculty, like, you know, we're trying to do the best we can, you know, to make the best out of a cruddy situation. And, you know, some of us may have been more effective, some may have been less effective, but even the ones that are possibly more effective, it still doesn't replace that in-person instruction, connection, interaction. I don't think we've found a way to emulate that online well, at least not yet. Maybe Oculus can give every student a headset and we can all meet in a Super Mario Bros. 3 themed world. That might be better in-person interaction. But until we go Full Metal Ready Player One school time, you know, I think in-person is going to be the way to go. Once we can Ready Player One the situation, then it'll be fine. but until then, I don't think we'll be able to replace the in-person interaction. But speaking of Ready Player One, this will circle back to the thing I was saying earlier. My brother's graduating from Berkeley, right? He's taking his finals this week, and then commencement would have been next week. It's been canceled. But a group of Berkeley students have built a gigantic Minecraft server that they've named Blockly, and it in this server they've made a like exact replication of UC Berkeley's campus, and they're planning on inviting everybody to join their Minecraft server for the commencement this year of 2020. And so we have an Xbox, and so my brother's going to attend his commencement on the Blockly Minecraft server for Berkeley commencement 2020. Yeah, totally. My brother's going to be doing it, and he was telling us about it, and my kid who's 9 was like, "Uncle Aaron, can I go to commencement with you?" and my brother was like, "Yeah, totally. It's, you know, friends and family can add too." It is so rad. I'm gonna be not playing. I'm not gonna have a controller in my hand, but I'm gonna be filming it on my phone for my parents so they can watch my brother graduate Berkeley on Minecraft. Anyways, it's moments like that too that it's like, oh, this whole situation sucks, but then some humans get really creative and still find ways to bring a smile to your face. So, you know, it may be not all good, but it's also not all bad either. For real. That is the truth. Oh, dude. It was absolutely my pleasure. Thank you so much for dropping in. I so appreciate it. These office hours have been kind of lonely lately. And I so appreciate the interaction. I miss all of you guys to death, and I hope that you're surviving the Rona 2020 quarantine as best you can. But anyways, I think I'm gonna call it a night there too. Mallory, thank you for the awesome questions. Raj asked some good ones earlier as well. Again, keep an eye out on Canvas. I'm going to be posting more about the exam once combined with when. Once I have more to say about it, I'll give you more specific problem breakdowns once I've finished. And but I would, in the meantime, I would focus studying on the SN1 lab, possible nucleophilic substitution stuff, and then radical chlorination GC stuff is the main inspiration I'm getting so far, unless I get some sort of strong direction from Max. That will probably be the heart of the test. So anyways, thanks for dropping in, and I'll catch you guys on Wednesday. Later.